Hi, and now let's continue with transfer learning. So transfer learning is one of the core properties of convolutional neural networks and one that has maximized their usefulness for practical applications. So what does transfer learning stand for? Assume we have two datasets T and S. So the dataset S for source is basically fully annotated and has plenty of images, and this means that we can actually build a pretty accurate model on this data. Our dataset T, on the other hand, is much smaller and not as richly annotated. So we've got very few images that are annotated by a human. So in that case, this will be a problem. We cannot easily train from scratch a convolutional neural network, especially when the annotations in our target set do not overlap with our annotations in the source set. So in that case, what we can do is we can apply transfer learning. More specifically, we can use our source model to improve our target model. So why do we want to use transfer learning? Well, basically, the problem is very simple. A ConvNet has usually millions of parameters, and on one hand, and on the other hand, our regular data usually are much smaller. They're not like millions and millions of pictures, and even more so, they don't contain that many annotations. They're not richly annotated. So what we can do is we can still train a convolutional neural network without overfitting by using transfer learning. It turns out that convolutional neural networks are particularly good in transfer learning, specifically because, as we saw, image statistics are shared across images. So not only just across the images in the same dataset, but also across datasets. Speaking, of course, for natural images. If our target set contains images from, that are not natural images, like medical images, then we might have too much of a domain difference. Still, some transfer learning could be possible. Generally, the idea is that we pre-train our neural network on dataset S, on the source dataset, and then we can either fine-tune or use our source ConvNet as a feature extractor. So for the first solution, we fine-tune our model HT to the source from the source domain to the target domain. So what we do specifically is that we assume that the parameters that we trained on the source training set is a good initial solution, and then we can use them to initialize the parameters in our for our ConvNet that we are training on our target dataset. We don't have to initialize all the layers. This is a choice that we can make. This is a good choice if your source dataset is very large and your target dataset is small, but relatively small, so not too small. And of course, a big question is which layers to initialize and how. I distinguish four different. We group the layers in a ConvNet in four groups. The first one is the classifier layer to the loss. When we've got very, very few pictures, very few images, very few annotations, so it's really hard to train anything from scratch, then it does make sense to only focus on the loss layer, on the the final classification layer, and keep all other neural network layers fixed. So we only change the final classification layer. And again, here we have to distinguish two cases. If the labels between the source and the target are the same, then we can just fine-tune. We can start with a classifier weight parameters as initialization, then change them a bit for our specific new target images. If, however, we've got different labels, which is the most frequent case, then we have to delete completely the layer of the classifier, keep all the rest of the layers in the neural network fixed. We delete the classification layer and we initialize it randomly again and train that only, that layer only. The second group of layers is the fully collecting layers, and they comprise the most usual case in terms of transfer learning. So if you have a bit more data, so not just a few, then it makes sense to fine-tune these layers first. If the nature of the data, the domain of the data is very different from our source, then it might make sense to even delete and randomly initialize from scratch the layer before the classifier. What is important here to realize is that the fully connected layers combine spatial layers, right? So they're trying to combine them in order to capture semantics. That's why when the domain difference between the target and the source is too large, we have to delete. We have to consider deleting also the last layer. When we have even more data, we might also want to consider fine-tuning the upper convolutional layers. So basically, we keep the low ones fixed, and we update everything above that. However, this is more for when we have got lots of data, and it really makes sense only if we expect any big differences between the target and the source. Otherwise, these mid-level spatial features like faces and wheel detectors are probably pretty reusable for different data sets. These mid-level spatial features capture more generic information, and fine-tune can pay off if we have enough data. Otherwise, it's not really going to give you much. Lower convolutional layers like Conv1 and Conv2 capture such specific information like edges or circles or corners that these features, one way or the other, are always going to be reused. It's not going to give you much to fine-tune. Of course, if your data is completely different, again, like medical images versus natural images, then these need to be retrained. In that case, you might need to consider whether we should even fine-tune or just train from scratch with random initialization. So how to fine-tune? For layers that are initialized from your source model, you have to use a mild learning rate. The reason is that these parameters are already near convergence. So if you use too aggressive of a learning rate, you might overshoot. So something around 0.01 makes sense. If you start with 0.01 originally, dividing by 10 makes sense. For completely new layers, you use a more aggressive learning rate, basically the same type of learning rate that you would normally use. The problem is that if it's too small, like if you're too conservative when with the learning rate for completely new layers, you might have very slow learning, and that can also cause problems because the rest of the network is near a solution, and then your new layers are very far from one. A learning rate of 0.01 is usually a good choice in my experience. In general, if the datasets are very similar, you only need to fine-tune the fully connected layers. Very similar in the sense that they capture similar natural images, etc., not necessarily similar classes. Whereas if the datasets are very different, like for instance, like object classes and traffic signs, maybe you can also fine-tune more layers. The second solution, which is a bit more radical, is to use the source model as simply a feature extractor. So you store your convolutional activations or your fully connected activations, and then you pass them through a regular classifier. This is basically similar to just retraining the classifier's loss, and this is useful. This makes sense when your target dataset is very, very small. Like again, we discussed the case about the classifier loss. Or when you have the resources, of course, to train a deep network from scratch, or if you don't care about the best possible accuracy. It's going to give you still pretty solid numbers. So which layer should you train? Well, like what does each layer contribute? Well, generally higher layers capture more semantic information. So these are good for high-level classification, so for object classification, whereas lower layers appear to be capturing more basic information, more like textures or colors and shapes. So if you want to do image-to-image comparison or image retrieval, where you don't really care about the semantics, what the picture depicts, but more like aligning things or like low-level operations, then focusing on lower layer features makes sense. So I will close this. We close now this lecture today with a summary. So today we discussed about convolutions and about what makes images special. We discussed about translearning, and we discussed also about ways of visualizing our features. Thank you.